If you're stuck between speed and relevance, two-stage retrieval is the standard escape hatch. We'll retrieve candidates fast, then re-rank a small list for a big jump in top results. Maybe your search returns lots of noisy hits or is too slow when you try to rank everything. By the end of this video, you will understand how to recall a cheap set of candidates in Python, and then re-rank just those with smarter signals, so your top results improve without killing latency. This pattern is pragmatic and easy to prototype with small code. I'm Professor Pi, teaching search and IR from basics to advanced with simple, concepts-first Python that helps you solve bigger, real-world problems. Two-stage retrieval solves a common pain. Scanning and scoring 1,000,000 documents for every query is too slow. If you instead grab a small pool of plausible candidates and then spend more compute on that pool, you get better top results for much less time. People use this in question answering, FAQ bots, and search where latency matters. Success looks like better precision in the first 3 results while keeping response times low enough for users. Intuitively, think of a librarian who first thumbs the index to find promising books, then reads the introduction pages of a few to decide which to hand you. The recall pass is cheap and broad. The re-rank pass is more expensive and precise. Strengths are speed and focused accuracy. Weaknesses are that a bad recall stage can drop the correct answer before re-ranking ever sees it. We will build a tiny toy pipeline. First, we make a cheap boolean recall. Then we swap to an inverted index. Next, we re-rank with a phrase signal. Then we add IDF weighting. Finally, we combine these pieces into a full 2-stage function that returns top texts. This keeps each idea isolated and easy to follow. Now we'll run a cheap, literal recall. This snippet builds a tiny corpus and runs a fast Boolean recall. The function toke lowercases and tokenizes both the query and documents into simple word tokens. We scan all documents and create the list C by checking if any query token appears in each document using a set intersection. This is a cheap recall-only pass that produces candidates without ranking them. The printed list is capped to 3 to mimic a recall pool size limit. The output shows which document IDs are even worth considering next. Here, out equals 01 highlights matching candidates. After that initial pass, I explain what each part does, top to bottom. Recreate a small list of document strings and a short query string. The token function splits on whitespace and lowercases, so punctuation and case are ignored in this toy setup. Then we loop documents and build a set of their tokens to test membership against the query tokens. The cap of 3 is the one knob you can change to fetch more or fewer candidates for the re-ranker. This fast scan is cheap for tiny corpora and useful as a baseline. Next, we'll build an inverted index to speed recall. This snippet constructs a minimal inverted index to recall candidates fast. The dictionary IDX maps each token to the list of document IDs containing it. For the query, we take the union of posting lists for its tokens, sort for stability, and cap to 3 to simulate a bounded recall pool. Using the index avoids scanning the entire corpus on every query while keeping the candidate set focused. Increasing the cap widens recall, but may cost a bit more latency. The printed value shows how many candidates entered the pool. Out equals 2 means 2 IDs survive the recall filter. Looking through the code, we first iterate documents and append each document ID to every token's postings list. For a query with multiple tokens, we gather all postings, take the union to avoid duplicates, then sort so results are reproducible. The cap is applied after sorting to emulate a fixed size recall buffer. This pattern scales well because the index lookups are proportional to tokens touched, not the full corpus size. Now we'll add a simple reranker that recognizes short phrases. This snippet re-ranks the recall pool with a simple phrase-aware score. We form PH from the first two query tokens to represent a cheap phrase signal. The list of stores token overlap counts for each candidate ID in C. Then S adds a 0.5 boost whenever the phrase appears in the document text. We sort by the boosted score and keep the best few IDs as R, breaking ties by document ID. Raising the boost emphasizes exact phrasing. Lowering it favors looser overlap. The printed ID is the best re-ranked candidate, showing which document currently leads. In code, we compute overlap by intersecting query tokens with document tokens and counting matches. Then we check whether the two-token phrase appears verbatim in the document string, and add the fixed boost when it does. Sorting uses the combined score and a stable tiebreaker so the output is predictable. This reranker is cheap and catches cases where exact phrase ordering matters for relevance. Next, we'll weight matches by how rare the matching terms are. This snippet adds IDF weights to reward rarer terms in re-ranking. We build the vocabulary V from all tokens, compute document frequencies DF across docs, and derive IDF so uncommon tokens carry higher weight. For each candidate ID in C, we sum the IDF values of the overlapping tokens with the query to get an IDF weighted score. This favors documents matching distinctive terms over generic ones, offering better precision at the top. Larger corpora increase IDF contrast, further prioritizing rare matches. The printed value is the best weighted score rounded to 2 decimals, indicating stronger R. Concretely, the code first tallies how many documents contain each token to compute document frequency. Then IDF is computed as a simple inverse function, so tokens present in fewer documents get larger IDF. For each candidate, we sum IDF for any query token that appears in that document. That single summed score is a compact but effective re-ranking signal that often outperforms raw overlap in noisy collections. Finally, we'll combine recall and re-rank into a top K function. This snippet assembles the two-stage pipeline and returns final top K texts. We score each candidate by summing IDF over query term overlaps, then add a small 0.3 phrase boost when the query phrase appears. Sorting by this combined score yields a stronger ranking on a small recall pool, avoiding heavy scoring over the full corpus. The list final returns the top K document strings, ready for downstream use or display. Increasing K surfaces more results at slight precision cost, while lowering K sharpens the top. The printed list confirms the end-to-end ranking result. The pipeline code runs the inverted index to get candidate IDs, computes the IDF weighted overlaps, applies the phrase boost if applicable, and then selects the top K by score. This mirrors real systems where you first filter to a few hundred or fewer candidates, and then run richer scoring on that subset. It keeps compute focused where it matters. This toy flow maps directly to production ideas. Use a fast ANN index instead of the tiny inverted index for millions of docs. Replace the IDF sum with a neural reranker when you need semantic matching, but the two-stage shape stays the same. Recap: two-stage retrieval first recalls cheaply, then re-ranks precisely. Use it when you need low latency and high top K quality. One caveat: if your recall stage is too narrow, you can drop correct answers before re-ranking. Next step: pick one parameter to tune and measure trade-offs. For example, increase the recall pool cap and track top K accuracy and latency. If short, practical IR helps, subscribe and watch the IR videos.